So here's a bunch of results for the Landauer erasure work statistics stuff. Well, there's actually no work statistics stuff so far. It's just been mostly just checking for convergence in the system dynamics. So the three main things that I'm changing are the coupling strength to the bath, which is given by one of these values in this list, the amount of time that it takes to perform the protocol, and the protocol is starting from some initial energy splitting given by this black line here. I either go to one of these three coloured lines and back again. So those three coloured lines are given by this maximum energy splitting epsilon tau, and it's one of these three values, which is a multiple of the splitting, of the peak location of the spectral density. So either equal to it, twice as much, or three times as much. So I start off by looking at convergence with respect to the time step and precision, basically just for every combination of the coupling strength, protocol time, and maximum energy splitting. And I think the one that we're mostly interested in is how it preserves the trace, which is going to be this top left-hand one here. All the other results are just pretty much exactly, they're not exactly the same, but they're pretty much exactly the same for the numerical parameters that I test, which are up here. And the only thing that differs really is how well the trace gets preserved. And in all cases, the best one is going to be dt is 0.01 and p is 13. So that reduces the trace the least during the protocol time. And all of these errors in the trace are of the order 10 to the minus 8, so it's pretty small. So if I just cycle through a few values, you can see that as I increase the protocol time, which is what I've done through these few slides, the trace gets worse and worse, which makes sense because we're propagating for longer time, so there's more likely that errors are getting built up. But even still, with this line here, which is dt 0.01, p is 13, the trace remains pretty close to 1 at all times. And then we just do the exact same thing, increase the coupling strength again and again and again. So this is maximum coupling strength, maximum time. And even here, the trace is preserved pretty well. It doesn't get below 10 to the minus 8. But it doesn't, how do I say that? The error doesn't get worse than 10 to the minus 8 during the protocol time. So then I just do the exact same thing again, except now with the different value of epsilon tau. So I now go, instead of going to the peak and back, I go to twice the peak location and back. And just cycle through the exact same thing again. And basically all these plots show is that dt is 0.01 and p is 13 is, from my opinion and estimation, a good set of numerical parameters to start testing things with for the work statistics. So I'll just quickly cycle through everything because it's not really that interesting. And then this is the convergence again, but now we go all the way to 3 times the peak location and back again. So these are faster protocols in the sense that the change in energy for a given amount of time is larger because we're going to larger values of energy in the same amount of time. So again, we just increase the coupling strength each time and then increase tau. And again, even with the largest coupling strength, the largest protocol time and the largest energy splitting, we still have fairly good preservation of the trace here. For some reason, it starts to increase rather than decrease for certain parameters. I'm not sure why. But again, the order of the error is 10 to the minus 8, so it's not really that big of a deal. So from what I can see from this, the results look converged with dt is 0.01 and p is 13. So now I use these numerical parameters and look at particular changes in the results for, say, first of all, we're going to fix alpha and then we're going to change the protocol time. So here we have the weakest coupling and we have the smallest energy splitting. So we just go to the peak and back again here. And then we can see how the results change as a function of the protocol length. So the most interesting one is this little inset down here, which just shows the final value of the target overlap splitting. So if we focus down here and look what happens as I increase the coupling strength, then what happens is as the coupling strength gets larger and larger, then shorter protocol times give better results. So I don't know what that means, but I'm sure there's something there. Okay, so now I increase the splitting, so just go to the orange line and back, and then just do the exact same thing again. So increase the coupling strength, and once again, the shorter protocol time given in blue is the best one. And then finally, we go all the way to 3 times the peak location and do the same thing again, and we see the same behavior. The only difference being now that all of the protocol times are not doing too badly, whereas when the final or the maximum splitting was at the peak location, most of these were actually off this set of axes. They were lower than 0.99. So it seems like for a larger value of the maximum splitting, the protocol seems to do better at erasing the qubit. So now we fix the protocol length and vary alpha, so basically just doing the opposite thing. And then here what we see is for a short protocol time, so this is tau is 100, weak coupling is the best. And that seems to be the case for all of these as well. So even for the longest protocol time, which is tau is 800 right now, the weak coupling is the best one. And now we just do the exact same thing again, except we've changed the maximum splitting. So that first one that I just showed was going up to the peak and back. Now we're going to twice the peak and back, and we see very similar behavior again. Weak coupling seems to be doing the best. And then finally we go to 3 times the peak and back, and surprise, surprise, we see similar behavior at long protocol times, that weak coupling is the best. Alright, so now I fix alpha and tau and change the maximum energy splitting. So here we start off with weak coupling, and then we'll cycle through the different tau values, and then in the plots we show the different energy splittings. So longer protocol times, which is what we have here, then larger energy splittings are better. And then we'll increase the coupling strength, cycle through tau again, and again we see that the larger splitting is better. Increase the coupling strength again, and we see the same thing. Increase it again, and we see the same thing. And this is the maximum coupling strength that we test, and we do the same thing again, and we see that for the largest coupling in the longest period of time, we want the largest energy splitting possible.